In our last lesson, we looked at factors that influence the rate of reaction. What can we do to speed up and slow down chemical reactions? In this lesson, I want to look about how are reactions measured in terms of rate anyway. I know that if I'm in the car traveling to Winnipeg, that I would measure my rate in terms of kilometers per hour. If I was running down the hallway, meters per second might be more appropriate. We always measure rate in terms of something changing over time. And in a rate of a reaction, what typically we see changing is the concentration. How is the concentration of my reactants changing as it disappears? How are the concentration of my products changing as they appear? Concentration is often measured in molarity. So we might measure rate as moles per liter per second, which may also be written as moles per liter second. Consider the simplest reaction we could possibly have. Something A turns into B, a simple rearrangement of molecules with one reactant and one product. I might consider how the rate changes in terms of the negative of the change in A, my reactant, over time. Now, the reason there's a negative there is because, of course, A is disappearing. So if I get less and less and less per unit time, it would appear to be a negative rate. Putting a negative sign here would cancel that. It doesn't make sense to be moving in negative rate. But a simpler way of writing it is rate is equal to some constant K times the concentration of A. K is a rate constant. Rate constants are numbers that allow us to put an equal sign in an equation. Without the rate constant, I would have to say that my rate is proportional to the concentration of A. You may remember that as we have a lower concentration, we have a less chance of collision and our rate would slow down. Over the time that a reaction occurs and my reactants get used up, my rate should slow down. So to find the rate at any one instant, I need a modifier, and K is that modifier. It allows me to use the equal sign. Rate is often substituted with the letter RR for reaction rate. And if I write RR equals K times the concentration of a reactant, this is a rate law. The square brackets means concentration of. Square brackets are a specific form of chemistry shorthand, and they have a different meaning than the rounded ones. Some rate laws have exponents or powers in them. In rate law chemistry, we call these the order of the reaction. If the rate law for a particular reaction was reaction rate equals K times the concentration of A, and we don't see a number, so we'll assume it's a 1, that's called a first order reaction. If our rate law works out to be K times the concentration of A squared, we call that a second order reaction. At this point, we're just learning some of the vocabulary that is used when describing rate laws. Momentarily, I'll explain to you why rate laws are important and how we figure out what they're going to be. Suppose that I have a reaction that is more than one reactant. In this reaction, I have two things reacting, A and B, and they're forming multiple products. Well, when we have more than one reactant, we multiply their concentrations together. All rate laws start with reaction rate equals K times. Then we multiply K times the concentration of the reactants. And each reactant will be to some order, some power, called the order of the reaction. The interesting thing is we will never know what K is going to be or what this order might be until we've done experiments to figure it out. And we have to figure this out every reaction that we do. But this would be the general setup for a reaction. So for a reaction that has both A and B, I might assume that reaction rate is K times the concentration of A to some order A times the concentration of B to some order B. If I were to tell you that this is a one-step reaction, and I would actually have to tell you that, you can't assume it. But a one-step reaction means that whatever A is hits whatever B is, and all at one fell swoop, every bond is broken and every new bond is formed. If that was the case, then the balancing could be used as my orders for reaction. Now this is very rare, and it would be called a simple or single-step reaction. And sometimes I'm going to tell you that that happens. Mostly we cannot assume it. But for the point of understanding some of the vocabulary, in this case we will. The order for the reaction then is A order in A, B order in B, and the overall order of the reaction would be the sum of A and B. So for example, suppose A is squared and B is to the power of 1. I don't see a 1, but we know that mathematically it means the same thing. Then this reaction is second order in A, first order in B, and 1 plus 2 is third order overall. And again, at this point, we are just talking about what are the words involved in a rate law. Why are we even doing this anyway? If I was using this particular example of A squared times B, what would be the effect of doubling A or doubling B? Well, let's consider this with the most simple numbers that we can pick in our heads. We're going to use the numbers 1 and 2 because it allows us to do some fast mental math. So let's assume then that for this particular reaction, the rate constant is 1. And let's assume that we're going to start with 1 mole per liter as the concentration of A, and according to this equation we square it. And let's assume that we start with the concentration of B also being 1 mole per liter. Again, these are the simplest numbers we can think of. 1 times 1 squared times 1 would give me a rate of 1 mole per liter per second. Now in this case it'd be moles cubed per liter cubed per second, but let's not worry about the units. My rate would be 1. How does my rate change if I double the amount of A? Well, keeping everything else the same, but doubling the amount of A. 2 squared is 4 times 1 times 1. My reaction rate would now be 4 times as fast. What if I doubled the amount of B? Well, going back to the original values, but doubling only B and nothing else. By doubling only B and nothing else, 1 times 1 squared times 2, I get a rate of 2. It's twice as fast as the original rate. So if I were working in an industry where I had to buy some more of a certain chemical in order to increase profits, I would find much more effect by doubling the amount of reactant A than I would doubling the amount of reactant B. Let me give you an example that you might relate to better. C2H5OH is the chemical formula for ethanol. Ethanol is the kind of alcohol found in drinking alcohol. When you internalize or drink ethanol, your body metabolizes it by burning it. It burns it in the mitochondria of your cells. We breathe in oxygen that's used to burn the methanol. That produces carbon dioxide that we breathe out, and water. The energy used gets used by the body. What would be the rate law for this reaction? Well, all rate laws start with RR equals. We know there has to be some rate constant K, and we're going to multiply this by the concentration of my two reactants. The first reaction is C2H5OH, and the second reactant is oxygen. We know that these reactants have to come to some order, and I don't know what they're going to be, so I'm going to call them X and Y for now. We're just going to leave placeholders here. So this would be a rate law for the combustion of ethanol. It's important to note that although a chemical equation has plus signs, a rate law is only multiplying. This is a sentence that tells us what's happening. This is a mathematical equation. The math equation is all multiplying and powers. There is no plus signs in it. So I wonder what the rate law, the power order of the reaction would be in terms of ethanol or in terms of oxygen. I'm going to let you know right now that orders are always small whole numbers, most commonly 0, 1, or 2. In rare occurrence, you might find a 3 or a 4, but we're going to be tending towards small whole numbers for our values for x and y. I wonder what the order of the reaction would be in terms of ethanol. At a conference I was at with a group of teachers, they asked this question of us. Most of us teachers, without thinking about it too much, incorrectly guessed that we figured it would be first order in terms of ethanol. Let me explain to you what the order actually is and why. Let's assume for a minute, like we did in the last example, and start with all concentrations of 1 and a rate constant of 1. Again, I'm going to show you how to figure out what the actual numbers are coming up. But for the point of argument here, 1s are easy numbers to manipulate in our head. So substituting the number 1 for the rate constant and for our concentrations, we can see that regardless of the values we put in place of x and y, that the reaction rate would be equal to 1. That the ethanol would be metabolized at 1 mole per liter per second. How does this change if we change the order? If we assume, like most of the teachers did, that our order was a 1, and we know that we started off with 1 mole per liter of ethanol, then my rate would indeed be 1. But if I drank twice as much and had 2 moles per liter, then my rate would double to 2. If I drank 3 times as much and changed this to 3 moles per liter, 3 to the power of 1, then my rate would increase to 3. By this logic, the more you drank, the faster you'd get sober. Now, I'm going to let you know that purely in the interest of scientific inquiry, I have done some personal research into this, and I can tell you it is not possible to drink yourself sober. The more you drink does not mean you get sober any quicker. If we were to change this to a 2 and make it a second order reaction, 1 squared is still 1, 2 squared is 4, 3 squared, 3 times 3 is 9. You would get sober even more quickly. So the larger the order, the greater the impact on the amount would have on the rate. And clearly, most of us have some understanding that this is not the case. It turns out that in terms of the amount of ethanol, it is a 0 order reactant. Anything to the power of 0 is just 1. So 1 to the power of 0 is 1, 2 to the power of 0 is 1, 3 to the power of 0 is 1. The rate at which your body metabolizes ethanol is independent of how much ethanol you have consumed. The rate, in fact, is entirely dependent on the amount of oxygen. In fact, the more oxygen that you can bring into your body, the faster that the ethanol will be broken down. So now we can see the importance of understanding what rate constants are. We need to figure out how we figure them out, and how do we figure out what the order is going to be. I've told you we can never assume the rate or the rate constant for a reaction. We have to do experiments. Consider this reaction where C2H4Br2 reacts with 3 iodide ions to form C2H4, 2 bromide ions, and a really strange I3 iodide complex. This reaction, if it were to take place in one step, would require all 4 of these particular particles hitting each other, and at the same time that they hit, all the bonds would be broken and all of these particles would be formed. That's not very likely. In fact, through scientific experimentation, what we have found is that this reaction happens in 4 steps. At the grade 12 level, I will not ask you to figure out what the steps are in a reaction. This is the kind of information that I would give you. This is called a reaction mechanism. A reaction mechanism is the single individual steps that occur to cause a reaction to happen. In this particular reaction mechanism, what we notice is that the first stage is the slow stage. The remaining ones are all quick. The slow step in a reaction mechanism is called the rate determining step, regardless of where it occurs in the mechanism. It doesn't matter if it's the first or second or last step. The one that is slow is labeled the rate determining step because it sets the rate for the rest of the process. How do these 4 steps account for the overall reaction that we notice? Well, you'll notice that the C2H4Br2 reacts with one of the iodides. That forms C2H4Br- and IBr. This C2H4IBr- then immediately decomposes to form C2H4 and Br-. It was made and then destroyed. Species that are first made and then one step and then used up or destroyed in another step are referred to as intermediates. This can be canceled out of the equation because it will no longer appear. We notice that the IBr made in step 1 gets reacted in step 3. It's first made and then destroyed. It is also an intermediate. It's destroyed when it reacts with yet another iodide to form Br- and I2. That I2 that is made in this step is destroyed in step 4 when it reacts with yet one more iodide to form I3. This particular reaction has 3 intermediates. The overall equation is what remains. Before the arrow, we'll have the C2H4Br, and we'll have 3 iodides. After the arrow, we see that we are going to have the C2H4. You'll see 2 bromines, and you'll see the I3. Once we have canceled out all of the intermediates, everything that remains is the overall equation. The rate diagram for this reaction would probably look more like this. We notice that the first step was the slowest, so it would have the biggest hill. More specifically, it has the highest activation energy. The other 3 steps were faster and had lower activation energies. We find that the intermediates are formed at the end of each step and destroyed before the next step is over. This overall rate diagram would have originally probably been drawn like this. Let's take a look at the rules that are involved when we go to solve rate law problems. How can we predict what the value for K will be and the values for our orders? This reaction that we have here in blue and all the words in blue are an example of what a rate law question looks like. You'll notice that you've been given a balanced equation and you've been given data from several experiments where we have tried changing the concentration of the reactants and measuring the effect on the rate. This is what has to happen for us to be able to predict what a rate law is going to be. I'm going to give you each step in the process and show you how we figured it out. Step 1 is to write the general rate law for the reaction. All reactions take the form of reaction rate equals K times the concentration of each of the reactants to the power of some number that we're going to call the order. Because we don't know the order, I'm going to name them X and Y. Remember, this is all multiplication at this point. Step 2. We're going to compare 2 of these experiments. And we want to compare 2 of the experiments where only one of my concentrations is changing at a time. For example, if I compare reactions 1 and reaction 3, I noticed from reaction 1 to reaction 3 that I started at 1 molar and changed the peroxide concentration to 2 molar. I have changed the peroxide concentration by 2 times. I have kept the concentration of hydrogen iodide the same. This is important because only one thing must be changing. If I'm changing both concentrations at the same time, I don't know which one is having how much effect on the rate. I can only compare this at one thing at a time. When I change only peroxide, how does the rate change? Well, my rate went from 0.0076 to 0.0152. 7.6 to 15.2 is doubling. Now, if you move the decimal points over, it's usually reasonably easy to see because, again, we're looking for small whole numbers. If you don't see that quickly, you can always take the big number divided by the little number in your calculator. So now we know when we've compared two reactions where only one thing is changing. Step 3. We're going to use this comparison to solve for the order of the reaction. From our comparisons, we saw that the rate doubled when peroxide doubled, which we can see is to some order x. We know that K, which is a constant, has not changed, and we have not changed hydrogen iodide. So the only thing affecting the rate is peroxide. This is a simple math expression. 2 equals 2 to the power of x. The only value we can put in place of x to make this true is a 1. Again, these values will always tend towards small whole numbers. Step 4. We're going to repeat these steps to solve for the order on the other reactant. So we've already compared to see where peroxide changes. Looking for a case where hydrogen iodide changes and is the only thing that is changing. If I compare 1 and 2, I can see that hydrogen iodide is doubling, but peroxide is staying the same. It is important to remember that only one thing can be changing. What is the effect? Well, the effect, because I'm comparing the same two equations all the way across, is that my rate doubles. Again, using this to solve for the order, my rate doubles when K stays the same, when peroxide stays the same, and when the concentration of hydrogen iodide doubles to some value y. The only value we can put in place of y to make this true is a 1. We now know that this reaction is first order in peroxide, first order in hydrogen iodide, and overall, 1 plus 1, it is a second order reaction overall. Step 5. We can now write the actual rate law. We know from our math above that the order in terms of peroxide is a 1 and the order in terms of hydrogen iodide is a 1. I don't typically write number 1s in chemistry, and mathematically it makes no difference, but I am putting them here to show you that they are the values that we calculated in the step above. Finally, step 6, we can substitute any experiment, be it 1, 2, or 3, any of the data we have, into this rate law and solve for K. I chose to rearrange my formula first to solve for K, but you can plug the numbers in and then collect like terms. It makes absolutely no difference. We now have a mathematical formula, and we have a list of data that we can plug in that leaves only one variable, and that's K. Substituting the numbers into the rate law and rearranging to solve for K gives me a value of 0.76. Now, at this point, I want to let you know that values for K are all over the map. You can have 2 or 3 questions that are 0.76 or 0.02, and the very next question might give you a value for K of 8 million. Don't worry about it. K values are there to account for things like the energy in the reactants, the activation energies that are required, the temperature of the room, all the different factors that might influence the rate in a reaction. The pressures involved, everything. And so K values change constantly based on conditions. So when we get to this point, we can just rearrange and solve for K. Now that we've seen the steps, I'm going to do one more example with you. Here's a set of experimental data for a reaction between 2 reactants, A and B. I'm going to start by writing the general rate law for the equation. I know I have 2 reactants, and I know that they're going to have orders. I'm going to call them X and Y. Now I'm going to do comparisons. Looking for a case where only A is changing, I can see A changes from 0.1 to 0.3. That's an increase of 3 times when B stays the same. The effect on the rate to go from 0.02 to 0.06 is also 3 times. So my rate increases by a factor of 3 when K stays the same, when A increases by a factor of 3 to some value x, and when B stays the same. 3 is equal to 3 to the power of x. X is going to be 1. Solving for y, which is attached to b, I need a case where b is the only thing that is changing. B changes between 1 and 3, but also between 2 and 3. But I remember that I have to have A staying the same. So between reactions 2 and 3, A stays the same, and B doubles. It goes from 0.1 to 0.2. The effect on the rate is to go from 0.06 to 0.24. 6 to 24 is an increase of 4 times. So my rate goes up by 4 times when K stays the same, when A stays the same, and when B doubles to some value y. Now, the number that we can put in place of y is a 2. 2 squared is 4. Now that I know the values for x and y, I can rewrite my rate law. RR equals K times the concentration of A to the power of 1 times the concentration of B squared. This reaction is first order in A, second order in B, and third order overall. Substituting any one line of data into the equation, and out of habit, I'm going to pick the first one. My rate is 0.02. K is the unknown that we're going to solve for. The concentration in A is 0.1, which we know is going to be to the power of 1. And the concentration in B is 0.1, which I can see is going to be squared. Rearranging to solve for K, we get a value of 20 as our rate constant. And again, I told you the values for rate constants can be all kinds of different values and can be all over the map. I'm going to need you guys to practice solving for rate law problems. There are several of them in your Chemistry, Matter, and Change textbook, found on page 574 all the way up to 582. The page numbers are there. And there's some more at the end of the chapter on pages 586 and 587. There are also several more questions for you to solve on the third page of your workbook section with rate law calculations. The first 3 rate law practice problems at the top of the page are done exactly in the same format that we just practiced together. In the bottom 3, question 2A gives you the rate law and the value for K, and all you're practicing is solving for an unknown. You've already been told that it's first order in A and B, and you have your value for K. This is a plug and chug question, practicing rearranging equations. For question 2B, you must first use the first 3 given lines of data to figure out your rate law, to solve for your orders, and then to determine K. Nothing has been given to you. Once this has been done, you use that rate law that you've calculated to solve for the blanks under B and rate. Question C is a third and separate question entirely again. In this case, I've given you a rate law with lots of squares in it. Use the first line of data to solve for K. And then, once you've solved for K, practice manipulating with squares to solve for the blanks under A and B.